Welcome to lecture 16, analog microelectronic circuits, and in today's class we'll continue on MOSFET amplifiers. So far we discussed about common source amplifier. So we will look at a variety of common source amplifier in today's class. All right. So again, for the initial reference, I am considering the same circuit what we have done last time, which is this is V in and this is V out. This is RD and this is VDD. If your lambda is equal to 0, we can write the voltage gain AV as minus GM into RD. If your lambda is 0, it is RD itself. If lambda is not equal to 0, you will get the R0 term also in parallel. So now if I look at this gain, I am going to call this gain as open loop gain. Open loop gain. So we call this as gain always, but to define very precisely, I will call this as open loop gain. So if you ask me why the reason, so probably you would have seen some of the amplifier circuits, especially with respect to op amps in your first semester class, in your basic electronics class. So there we use some resistors in feedback, and whenever we use external components and if there are some feedback in the circuit, your gain will automatically change. So when there is a closed loop like that through resistors, we call it as closed loop gain. So as of now, you can see that there is no feedback or there is no connection between output and input. No portion of output voltage is fed back to input. There are no such feedback mechanism, and for that reason, for that very simple reason, we call this as open loop gain. I hope it is clear. I am calling this as open loop gain because there is no feedback elements connected to the circuit. Right. So looking at this gain expression again, say if I write GM, I know GM I can have different expressions, and one such expression is mu n Cox W by L into VGS minus VT. Right. Now, if you look at this gain expression, if you look at this GM expression, this mu and Cox term is otherwise called as process parameter. So this depends on the mobility and the Cox, the oxide capacitance. These two things, or this process parameter, basically depends on the fabrication process, or we call it as process, CMOS process. So it depends on the fabrication unit, or depending on the ability of the fabrication unit to get a Cox value, depending on the fabrication processes available there, this parameter is highly depending on, so we generally call this as process parameter. This depends on the fabrication process itself. Now, if you look at this term, this is VT, threshold voltage. We call this as threshold voltage, and this threshold voltage, no, when I look at mobility is having actually a dependency on temperature. So probably you would have learned that in physics also. It depends on temperature. So as temperature varies, there will be certain variations to mobility, and there is a relation exists between mobility and temperature. Now if you look at threshold voltage VT also have some kind of variation. So that again depends on the device physics. So VT also varies. This is also varying parameter. So if I look at this GM expression, in this mu and Cox is a varying term, this VT is a varying term. So if I look at these two together, I can say that GM itself is a varying term. GM is not a constant term, constant in the sense for a particular DC voltage, GM will be constant. But if there is a temperature variation, if there is any other process variations, there will be some variations to GM. So what will be the result of that? If there is a GM variation, ultimately there will be variation in gain. So since AV is minus GM into RD, now if there is a variation in GM, your gain will actually vary. Right. So why I'm talking about temperature here is, in most, when we go for especially for ICs, when we go for IC design and all, we will try the temperature from say from minus 40 to 120 degrees. So we will look at the performance of IC across a wide range of temperature, and in such cases definitely this is going to vary. So as a result, your GM will vary and gain will vary. So the simple point what I want to convey here is, Even though we have written gain for a common source amplifier as minus gm into rd, gain is no longer a constant value. Gain depends on gm, and if gm is varying, gain will also vary. Are you getting? Are you getting what I'm trying to say here? Can I get few response?
Yes, sir.
All right. Others can also respond in the chat box so that I'll know that you are with me. So the simple point what I'm making here is GM. There are some varying parameters in GM. So if those parameters vary with respect to process or with respect to temperature, GM will vary, and if GM varies, your voltage gain will vary. But we know that we always look for a voltage gain is something what we want is a constant, or we do not want the gain to vary for any system. Say if you are designing an amplifier, unless and until you need a specific application where you want some variable gain amplifier, almost all the other cases you want to have a voltage gain, a fixed value, right? So now if this happens, your voltage gain will vary, and that is not a good thing. Or we should come up with some circuit which can provide a more stable gain. If you look at this gain is varying, the gain is not stable. In that case, we can actually look at some other circuit which can provide a little more stable gain. So in that node, or with that objective in my mind, we are going to discuss about the next amplifier, that is CS amplifier, that is called as common source amplifier only, but with a resistance at the source. We call it as source degeneration resistance. We call this resistance as degeneration resistance, right? So common source amplifier with a degeneration resistance. So let us see what is this degeneration resistance. So that is our next amplifier, CS amplifier with source degeneration. So why are we going to the circuit? We are discussing this circuit because we understood that in the previous case the gain is varying, or since gain depends on GM directly, gain is going to vary. Now can you give me one solution? So how can I make gain more stable, or how can I make gain uh, not varying as the previous case, as this case? What can be one single solution for that? Can I get some response? Gain is varying because GM is varying. So now to make gain fixed or gain stable, yeah, make it independent of GM. Very good. Yeah. So we are actually going to make an effort. We are going to make an effort to make our gain independent of GM. Not exactly independent, but what we are going to do is we are making less dependent on GM. Right. We cannot come out of this GM as such, but we will look for a less dependency on GM. Right. So the circuit remains same. The circuit remains same as the previous case. This is V in, this is RD, this is VDD, and this is V out. But source is not grounded. Now at source you have another resistance which I call it as RS. Say we will consider the lambda equal to 0 case first. So now after discussing the method to find output resistance, and also after discussing common source amplifier, I hope you are in a position to derive the gain expression for this circuit. So uh, so what we want here is we want to find AV. AV is nothing but V out by V in. So can you guys draw the small signal equivalent circuit of this? So that is the so if we want to find gain, so whenever we say gain as open loop gain, this is again small signal gain, the gain of the circuit when you are applying a small signal to the gate of this circuit. So this is again we call this as small signal gain. So gain is for the small signals. So can you draw the small signal equivalent circuit? Small signal gain. So what is the first step? You have to draw the in order to draw the small signal gain, the first step is you have to draw the equivalent circuit of MOSFET. So What I'm drawing here is the three terminals of MOSFET, this being gate, this is drain, and this is source. Right. Now, for a VGS voltage, we'll have this as GM into VGS, and I'm not considering R naught. So this is the equivalent circuit of MOSFET. Now I have to modify this circuit with the given. I have to modify the equivalent model of MOSFET using the given circuit. So what is at source? At source, I have another resistance. I connect that resistance RS to ground. At gate, I have to connect V in. At drain, I have to connect RD, but we know that this VDD is a DC source. DC independent sources should be grounded. So I have to connect a resistance RD here, and this is V out. So I don't know whether you got the clarity on that. So whenever we draw small signal equivalent circuit, all the independent DC sources, whether it can be current source or a voltage source, independent DC sources will be grounded, because the reason is those independent DC sources are not changing. We are looking for the changing signals or changing parameters. So we will consider only the changing things on this circuit, right? Now, if you are finding output resistance separately, what you can do is you can actually remove the load resistance and you can connect the test source there. You can find what is Vtest by Itest. But when you do this, the circuit should be without the influence of any other sources. So that means you have to even short the input source also. So those steps should be very clear. You should not get confused, right? So can I get a response from you guys regarding the equivalent circuit what I have drawn now, what you are seeing on the screen, whether it is clear or you have doubts on this? If it is clear, give me a response and you can write the output voltage expression from this. If it is clear, please give me a response and write the voltage gain expression from this. I can see 60 participants and few responses are coming in. All right, yes. So since you are seeing everyone writing clear and yes, you are not forced to write clear and yes. If you have doubt, please you can ask. I can clarify it again. All right. So since I am seeing everything as clear and yes, I am going ahead. I'll write the expression now. You can also try with me in parallel. Hello.
Yes, sir.
Okay. Okay. All right. So you can try. I'll also write the expression here. So first I'll write what is V out. So what is V out? V out is the drop across RD. Now the current is actually flowing in this direction. So I can write it as plus minus in this form. So V out is minus GM VGS into RD. This is V out. Right. Now, what is V in? So V in is, you can see that V in is the voltage from gate to ground, because the reference is always ground, or the reference point is 0 itself. So V in is from gate to source, it is VGS, and from source to ground there is a drop across RS, right? So what I can write here is I can just mark this node as, say this node I am marking as VS, and if I write the expression I can write V in minus VGS minus Vs is equal to 0, right? Now what is Vs? Or I can write V in as the sum of Vgs plus Vs. Now what is Vs? Vs is the drop across Rs. What is the current flowing through this? It is GM VGS. is the current. So Vs is, I can write Vs as Gm Vgs into Rs. That's all. I'm substituting it back. So I can write Vin as Vin is equal to, I'll take Vgs to the right side, plus Vs is again Gm Vgs into Rs. Or from here I can write what is VGS, because VGS is Vin divided by 1 plus GMRS. So why am I writing what is VGS here? Because the equation what I have for V out is this. In this V out, VGS is an unknown, or I want to write VGS in terms of Vin and V out. So I can substitute back this VGS over here. So that will give me the result V out equal to minus Gm into Rd into, for VGS I'll substitute it as Vin divided by 1 plus GMRS, or voltage gain AV is equal to V out by Vin, which is equal to minus GMRD divided by 1 plus GMRS, minus GMRD divided by 1 plus GMRS. Any doubt in this? So when we started the discussion of this common source amplifier with source degeneration, I told that the aim is actually to make your gain expression less dependent on GM. Yeah, it should be independent, but at least it should be less dependent. Now you can see two GM terms here. So how the objective is satisfied here? What do you think? So I'll just take the gain expression here. AV is equal to minus GMRD divided by 1 plus GMRS. So I hope this whatever I have done as a small signal equivalent circuit analysis is clear, and we have arrived at the gain expression as minus GMRD divided by 1 plus GMRS. So initially I stated that the gain should be less dependent on GM, and now you can see two GM parameters. So uh, 2 GM in the expression. So how will you come to a conclusion?
So denominator is approximately GMRS, so you can cancel it and you can say that it's dependent on RD and RS.
Yes, true. We can do that. Okay, so I'll explain that. So if you look at this equation, it is minus GMRD by 1 plus GMRS. But now this GMRS, or the magnitude of this GMRS can be decided by the designer itself, because that depends on RS. So the value of RS will make GMRS, you will get a value for GMRS. Now, if that GMRS is larger than 1, right, say for example your GM is 1 milliamps per volt and RD is say 10k. If this is the case, sorry, not RD, RS, in that case you will get GMRS as 10, and 10 is very large than 1, or in the denominator 10 or 11 will not make that difference. So in such case I can approximate the gain expression as minus GMRD divided by GMRS, or that is approximately, this is an approximation, so that is approximately equal to minus RD by RS, right? So what I stated in the beginning is or the response even from your side is we want to make gain independent of GM, and by an approximation, yes, we have satisfied that gain is now independent of GM. Right. Now gain is the ratio of two resistors. Now what is the advantage, or what is the advantage compared to the previous case of AV of GM? So this is for your CS amplifier with a resistance in the source. We call that resistance as degeneration resistance. I'll explain you why we call it as degeneration resistance. Now the previous one what we had is minus GM into RD. So this is for CS amplifier itself. Now if you look at two gains, I can say that the gain of a CS amplifier with a source degeneration is less dependent or independent of GM. For that reason, this gain is comparatively stable. Right, this gain, the gain what you get from a CS amplifier with source region is stable, because the gain is simply the ratio of two resistors. Now if you want to have a gain of 10, or if you want to gain have a gain of 50 or so, you can actually choose the resistor values in such a way that you will get that gain. So nothing else is actually influencing the gain, or gain is relatively constant compared to the other case. Is that clear? Can I get a response?
Yes, sir.
Okay, yes. So please, everyone can respond in the chat box when I ask a question, because otherwise there is no method for me to what to say, to come to a conclusion that you guys are following me. Right. Okay. So let me go ahead and explain you about the output impedance calculation also. So as now you know how to calculate output impedance for any circuit. mm, Let us see, or let us see the calculation of output impedance in this case also. So so you have a circuit with you. So what is a circuit? I'll explain that as well here. The circuit is this. So now you want to find the output impedance of this circuit. So what will I do? I'll actually convert the circuit, or I'll apply the procedure what I know. As per the procedure, the independent sources you should actually consider it as ground, since it is small signal analysis what I'm going to do. Now what you can see is this RD here, but RD is now coming in. So I need to find what is output impedance, the impedance seen from this node. Now RD will be definitely coming in parallel to that. So I will not even consider RD. RD I'll keep aside. I'll find the impedance and then I'll take it in parallel. So the impedance or the circuit what I'm going to consider is only this. This is V in, that also should be grounded. So this is M1 and this is RS. Right. Now how will I find the output impedance? I have to connect a test voltage here, V test, and this has to carry a current of I test. Right. So if you have an expression, if you have a circuit of this form, I think you already know what will be the answer, because this we derived in the last class. What will be the answer? The resistance Rs plus the resistance of MOSFET, which is R01, plus GM1 R01 into Rs. This is what I know. Right. Now in the previous case, or in the case if I am considering lambda equal to 0, if your lambda equal to 0, that means your R out, you can apply the same formula. What will be R out? R out will be equal to Rs plus lambda is 0, so your R naught is infinity, plus this also infinity. That means your R out is approximately infinity, not approximately, it is infinity itself. Right. Your R out is infinity. Now if R out, so since there was an RD, I can consider this as R out dash, right? And your final R out, I can write it as RD parallel R out dash, that will be equal to RD parallel to infinity, that is RD itself, right? So in the gain expression, minus GMRD by 1 plus GMRS, this was the expression. In this expression, this RD is actually R out itself. Now in the previous class we also understood that we can write gain as the product of GM and R out. In that case, the GM of the circuit can be written as GM by 1 plus GMRS. This is something extra. Definitely we can look at about this GM even later also, right? So I just compared with the regular expression AV equal to GM into R out. I hope yeah, this is what I am referring to. So I have written AV as GM into R out. So if R out is RD, whatever is left is the GM of the circuit itself. Right. So if this is clear, I hope this is clear. Okay, so we wrote the gain, we wrote the output impedance. What about input impedance? So these three parameters are generally we consider for any circuit. So input impedance here also it is infinity. What is the reason input impedance infinity? This is the point where you are applying input, but the input current is 0. Since your input current is 0, whatever resistance you measure will be infinity itself. So R in is infinity, R out is RD itself, and your gain is minus GMRD by 1 plus GMRS. Right. Okay. So if this is clear, I request you guys to find the voltage gain of a CS amplifier with source degeneration, but consider lambda not equal to 0. So if you have doubt in this, you can ask now. Otherwise, you can start.
Excuse me, sir.
Yes.
So can you please once again explain that?
Which one?
R out dash from R out dash, the expression you wrote now, sir. RS
Uh,
plus R. That was.
this one.
Yes, sir.
Yeah. Yes. What is the doubt, Mohan?
So actually, I didn't get that R out dash. How you got that RS plus R01?
All right. So did you watch the yesterday's video? What I have given 10 minutes video.
Yes, sir.
Okay, then you should be able to relate that. Let me go back to that. So this is the formula what we have derived, right?
Okay, sir. Okay, sir. I
No,
got
the
got
same
it.
thing. The same thing. Yes. Is it clear, Mohan?
Yes, sir.
Okay. Okay. Yeah. Okay. So now what I'm asking is, you guys can try this when your lambda is not equal to 0. So the circuit remains same. This is lambda not equal to 0. Hello, am I audible?
Yes, sir.
Yeah,
Yes,
yeah,
sir.
yeah. Please, can you guys try this? So there will be only one difference in the equivalent circuit. You should consider even R naught also, right? So I'll try here. You can also try in your notebook. So these are the three terminals of the MOSFET. This is VGS. So you'll have GM-VGS here. So this is the equivalent of MOSFET. This is the equivalent of MOSFET, and you can modify this. You can add this RS here. This RD this side, and V in here. This is V out. Yeah, this is your V out. So can you guys try? So how will you do? You can do the same thing as what you have done before, but the only difference is now you have one more resistance in parallel to your GM-VGS, right? So if you can convert this into, so this is a current source in parallel to a resistance, you can convert that into a voltage source in series with the resistance. So probably you can apply this. So if you have a current source, in parallel with the resistance. If this is I and this is R, this can be equated to a voltage source of this polarity in series with the resistance. So this is IR and this will be the form. So you can apply this and you can redraw the equivalent circuit and you can proceed with the analysis. So I can help you guys. So what will be the voltage source here? It will be an independent voltage, sorry, a dependent voltage source of the value Gm VGS R0, and the resistance will be R0 itself. So if I redraw the circuit, this is gate side, this is drain, and this is source. And now here we have a dependent voltage source of value Gm VGS into R0. This is that series resistance R0. Now this side you have VGS. This is the equivalent of MOSFET. Now when I modify this as per the given circuit, I have to add an RS here, RD here. This is V out. So now you can try this in different way. You can write the expression yes, Kiran, R0 parallel RD plus RS plus GM. RS plus GM RS dash into there is a small correction for so I'm asking for the gain expression. Did I ask you? No, I forgot. I asked you to find the gain expression or R out expression. Find the gain expression first, and then we can write. Yeah, then we can look for the R. So R out is anyway known, right? R out expression will be same as R0 plus R0 1 plus or R0 plus RS plus GM R0 RS. That is clear. And the entire thing will be parallel with RD. Yeah, Kiran, I can clarify. I think you got a small confusion somewhere. I'll clarify that. Yeah, so first we'll write the gain expression. Now you can approach in different ways. So one simple way is, so anyway we know that current is actually flowing in this direction. So I'll take this as current as I, and I will write output voltage expression. So V out can be written as minus I into RD. So why I have taken small I is since it is a small signal current. There is no DC current in the circuit now. We are looking for small signal current. Yes, Kirtana, I think it is not directly minus GM R0 parallel RD. Yeah, the problem is probably you would have see this R0 and RD are not in parallel. This is one mistake generally observed. You can see that your RD is from this point to ground, but your R0 is from between your drain and source. If your source was grounded, your R0 and RD will be in parallel. Yes. So now, since your source is not grounded, your R0 and RD are not in parallel, right? So I can write V out as minus I into RD generally. And how will I write I? I is the current in this, right? So, so in this loop, if you consider this loop, the three resistances are R0, RD, and RS, and one voltage source is GM VGS into R0. So the voltage source divided by the resistance will give you the current in that circuit. So I can write it as GM VGS R0 divided by R0 plus RD plus RS. This will be the current. In that case, I can write V out as minus GM VGS R0 divided by R0 plus RD plus RS into RD. But now this is not the gain expression. Here again, you can see a VGS term in the V out expression. So I will make an effort. We'll try to get a value of VGS in terms of V in. So what is V in? V in can be written as V in is equal to, as before, it is VGS. I'm doing the same analysis what we have done for lambda equal to 0. The only difference is we have to just do this parallel current source with resistance is converted into a voltage source in series with the resistance. That is the only difference. Now I can write V in as the VGS voltage plus the drop across RS, that is I into RS. Or VGS can be written as V in minus I into RS. That means I can write in elaborate as V in minus I know what is I is GM VGS R0 divided by R0 plus RS plus RD into This is RS. The RS, the same RS we have to write there. From this I can get an expression for VGS. I'll get VGS as V in into, you can just cross multiply and get the answer, RS plus RD divided by, take VGS term to the left side and then divide it. So R0 plus RS plus RD plus GM R0 RS. Right. So now if I substitute VGS here, I can write V out as minus GM R0 RD divided by R0 plus RD plus RS. Now for the VGS, I'll put the same term here. So VGS can be replaced as this, V in into R0 plus RS plus RD divided by R0 plus RS plus RD plus GM R0 into RS. Right. So here you can see that this term and these both can be cancelled, and V in can be taken to the left hand side. Right. So if I'm doing that, I can get the expression for V out by V in as minus GM R0 RD divided by R0 plus RS plus RD plus GM R0 into RS. Right. So this will be the expression, or this can be written in different forms. So don't worry by seeing this big expression. We can actually understand this by just taking R0 outside. I can write it as, if I take R0 outside, it will be 1 plus RS plus RD divided by R0 plus GMRS. Right. Or this can be written as minus GMRD divided by 1 plus RS plus RD by R0 plus GMRS. This is the gain expression. So gain expression, you can even remember this formula or this one. Right. So what we have done here is we have obtained the voltage gain expression for a common source amplifier with the resistance. We call it as a degeneration resistance with the lambda not equal to 0. So this is lambda not equal to 0. That means if I put lambda equal to 0, you should get the same expression. What was the AV expression when your lambda is equal to 0? So when your lambda is equal to 0, what will happen? Your R0 will be infinity. That lead to your gain expression from this. So what will happen if your R0 is infinity? This term becomes 0 and it will be minus GMRD divided by 1 plus GMRS. Right. So this is for a CS amplifier with source region when your lambda is equal to 0. Now, how will you get the expression for CS amplifier in this case? For a CS amplifier, uh, RS is not there. So RS is 0. That means you will get the expression as minus GMRD. Right. So all are related. So the only thing is you have to just map and see how the expressions has come up. Right. So I hope this is also clear, or I can actually open for discussion now. Before that, I just want to write about the Rin. Rin is infinity again in this case because input is connected to the gate. Gate current is 0, so Rin will be infinity. Now you can find R out of this. This R out we have already obtained separately. So I'll explain that also now. So you can find R out. This should be grounded because this is a source. Now here you have to connect the test voltage. So for this setup, I know what is R out. So let me call it as R out dash. R out dash is R0 plus RS plus GM R0 into RS. Now to get the complete R out of the circuit, this should be in parallel to the RD because RD is anyway connected at the output. So this will be RD parallel to R0 plus RS plus GM R0 RS. Right. I hope that is clear. This is your R out expression. Yeah. Now, one more thing I just want to state here, why we are calling this as source degeneration is, degeneration is a word which is used with something called as negative feedback. So probably, I don't know whether you have heard this, we call it as regeneration and degeneration. So whenever we use a term called degeneration resistance, the meaning is that resistance is actually providing a negative feedback, right? We will deal with this in more details later, not now. So the one takeaway point is this resistance RS is actually providing a negative feedback in the circuit. That means if at all, if there is a variation happening to the input side, this RS resistance is actually uh, giving a negative feedback. So take it from me, this degeneration resistance, the name comes from because of it is providing a negative feedback. We will discuss about this in detail later. So now it is open for discussion. If you have doubts, you can ask. Otherwise, we'll wind up here. So thank you so much for joining.